All right, let's get started. Welcome to round 11, actually 12. There's not, I sort of noticed that the attendance is diminishing, or at least I get about half the people, I think, or a little over half. Problem is, you guys are the ones who come, and I want to mention this. I want to mention the people who are not here. But anyways, class participation is part of the grade. So you guys are, thank you for coming. Everyone should be coming. Spread the word. Okay, so today we're going to review our transmission types, discuss a little bit about layouts and dimensions, how the ballbot looks the way it does, how we got the dimensions to provide you in those sketches that we gave. We'll go through the full planar model. So we went through the single planar model and we were doing speccing of our motor. So now we're going to expand on that. And then we're going to hopefully get to derivation of our torque conversion and do a quiz. I haven't been able to make homework 3. I'm going to make that today during office hours, so we posted, and then I'll try to give you guys like 10 days or so, or 2 weeks to do it. We'll see how it shapes up and how challenging it is. But that should be done today. Eve is grading your homework 1s. Have you guys gotten this back yet? No? Okay. I sent him a note, but I haven't heard. You'll get homework 1 back soon, and then hopefully you'll get homework 2 soon. But okay, any questions about any of that stuff? All right, so this is where we were. Describe the flow of what we're learning. We've talked about transmissions, talked about rotary to linear, linear to rotary, different types of transmissions. And then we're going to begin kind of doing this more in-depth analysis of the geometry of the ballbot. After that, we're going to do mechatronics. That's kind of next week. So it'll be like sensors, IMUs, communication, and then dynamics and control. And that's when it's going to get hard. The control of the ballbot is pretty challenging. That's a little bit of a review. We talked about gear design. So if we're making a gear design, we might be using spur gears or bevel gears. And then there's a number of things you want to know ahead of time. So this would be after you've done your speccing, you know your transmission ratio, you know your motor you want to use. Now you need to package that transmission ratio. So that's going to be potentially involving gears. It might involve some of the other transmission types we talked about, but you have to set up that process by knowing some things about your design of your robot. How easy do you want this process to be? That's a big one for rapid prototyping. You have access to some pretty easy tools, make things pretty simple, but it could also be more challenging and send stuff to be machined. That takes a little bit longer. You know your transmission ratio, you know your loading and your torque required. All that happened in the speccing process. Geometry is very application specific. We're going to do some of that for the ballbot. And then range of motion also potentially very application specific. We talked through like different types of gears, spur gears, bevel gears. They all use kind of the meshing of these teeth. And the meshing of these teeth kind of define the geometry of the two gears that are rolling against each other. And it defines the transmission ratio. We don't need to know all of this anatomy, but we talked about a few of the dimensions that are going to really matter. The biggest being the pitch diameter, pitch radius. So the pitch radius, where is the pitch radius? What is it effectively? Yeah, so
halfway up the teeth.
Yeah, it's about right here, halfway up the teeth, and it's the dimension that we use when we think about these gears being circles. Those are the dimensions we use to define transmission ratios, diameters, etc. Talked a little bit about backlash. You'll see that in different types of transmissions. And then the pinion gear is a small gear, and the large one is just usually called the gear. This describes a little bit more of those dimensions. Sometimes when I convert to PDF, it does like strange things. One of the things it does is it like changes the shadow to be like a little bit more intense. Every so whenever I'm teaching, I'm like noticing all these little changes that happen when it goes from PowerPoint to PDF. But anyways, okay, so this tells us a little bit about the mechanics of these transmissions, how they relate to these different factors. Our transmission ratio N, which we defined from our speccing, is related to the different aspects: diameter, number of teeth, pitch radius, velocity. That kind of describes those relationships. And then conjugate action is just something that defines the kinematics of the two gears. It's really just a word you should know. That's how we define the relative velocities between the two gears, is through the concept of conjugate action, where the pinion gear is driving the gear. Oftentimes you may not have to actually build a transmission. You can sometimes buy them like what we're doing in this class. That's usually, if you could do that, it's usually better. Sometimes you can't do that because you'll be doing linear systems, which might require some packaging and geometry. But if you can just buy a motor with a transmission attached. That's what we did in this class. We bought this motor. And this is just from Pololu's website. So if you were doing this process, you'd be on your computer, going to websites, looking what's available, finding their transmission ratios, their relevant properties, and factoring that back into your design and analysis. So we kind of have done this for you in this class because we pre-selected that gearhead and motor from that original analysis that we learned. But this is a kind of a much easier path to developing a transmission ratio in your design, but it's not always possible. This is a rack and pinion and worm gears. Rack and pinion is essentially a spur gear transmission where the gear has an infinite pitch radius. So it turns rotary motion into linear motion. And you guys have seen these in kind of different applications like car steering. Worm gears is another option, and they're used typically when you want an extremely high ratio. It changes the axes of rotation by 90 degrees. But the things that are kind of helpful is that they generally have pretty good backlash characteristics because of their high ratio. But you don't see I don't actually see them too much because they're almost always like non-back drivable, or oftentimes non-back drivable. So we don't use them too much in robotics. We talked about screws. Screws are used a lot in robotics. It's often important to convert rotary motion into linear motion. So if we do that, we end up using, there were two types of screws, a lead screw or a ball screw. The lead screw is just like a regular fastener in a nut, essentially. And then a ball screw had the addition of ball bearings inside that were rolling around the shaft. And what did that provide? What's the difference between these two in the sense that there are balls? What does that really change? The type of contact? What was the change? Yeah.
Rolling contact versus sliding contact.
Rolling contact versus sliding contact. And that has a very large effect on the efficiency and back drivability. If you are designing with screws, you'll have to be able to convert between force and torque and rotary velocity and linear velocity. These equations to do that are here, and they depend on one primary characteristic of the screw. What is that characteristic? Yeah, the lead. What's the lead? Yeah.
The distance between each thread on the screw.
Yeah, the distance between each thread and the screw on rotation gives you that much linear distance. That's right. So these relationships are going to be important. But we see these a lot in robotics. You can buy them packaged together, and we kind of pass one around. You can just buy that off McMaster-Carr or Masumi. We talked about linkages, which are also very common in robotics. They were a little more complicated. They have many uses. Sometimes they do rotary to rotary. Sometimes they do rotary to linear. They have nonlinear and kinematically varying transmission ratios. So that makes it, that can be challenging, but it can also be exploited. There might even be some applications where in certain regimes or certain positions, you want a higher transmission ratio than in other positions. So that these can be exploited to actually be useful in the sense that it's not a nonlinear transmission ratio. Can anybody think of a system that has a linkage? Maybe a robotic system, ideally? Yeah.
The way like train wheels move, is that linkage?
Oh, yeah. I mean, like a steam engine.
Yeah, sure.
Yeah, a steam engine, yes, I would say that is a linkage. Or like a manipulator, or like, for example, construction equipment. Linkages are everywhere. And they can be, so what we talked about was 4-bar linkages, the most common, but they can be, many different bars. It can be 6, 7, 8-bar linkages, and the complexity of the kinematics goes up. Yeah.
Do they have to be like connected to each other and form, I guess, like a closed loop?
No.
So you any robotic arm would just be a linkage, right?
And you could call that a linkage. It wouldn't have the same properties as a 4-bar linkage, but it certainly could be considered a linkage and would have things like a Jacobian that varies non-linearly with angle. So there could be a bunch of nonlinear descriptions that would describe or follow a linkage, but I wouldn't say it's not usually used in the same way. Like a linkage is almost like a transmission generally.
Right, yeah.
And a manipulator might not, it is still a transmission because it's moving rotary motion into end effector linear motion, but it's a little different. I think you get it. Yeah, good question. And so, but I think generally the chains don't have to be closed. Okay. Did anybody go to this website? I kind of posted this website that has a bunch of different neat linkages that you can configure and watch. It's actually like kind of cool. It's worth like perusing. There's a ton of different types of linkages, and a lot of mechanical engineers have really studied them. So here's an example of slider crank. Does that look familiar? What uses a slider crank mechanism? An internal combustion engine. This is like exactly what we're talking about in this set of lectures. Parallelogram 4-bar. This is an input link. That's an output link. And we would kind of use that depending on what exact application we have. So L3 is the input, L4 is ground, L1 is the output. We defined the kinematics and the constraints that make this 4-bar linkage work. So this is essentially saying what? What was this? Like a
Pythagorean's theorem.
So we have a geometric constraint. It says like essentially the links can't change length. So they have to make up these triangles. And then we have some position and velocity constraints that we also went through. So this tells us, for example, if we had a set of links and we wanted to find what is this configuration? We have all the link lengths, we have this angle and this angle. What is this angle? And that could be found kind of using these equations, or a bunch of different geometric relationships exist. There's also a velocity relationship that describes how motion of one link is transformed to the other link. And so if you were designing a 4-bar linkage, you would end up looking at all of these equations, parameterized typically by their length or starting configuration, and then you would investigate all the solutions that exist for your application, and it would be a lot of solutions. Then you would have to look at something like other concepts that differentiate within those solutions. What might those other differentiating factors be? Let's say you have an application, there's 100 linkages that satisfy your desired kinetics and kinematics. What else is going to matter? There's one thing specifically we talked about yet. Packaging. Specifically, like how small can things be realistically? There's only, our machines have tolerances, our manufacturing prototypes have tolerances. So there's only, there is a finite limit on how small things can get before you'd end up having trouble. So you would search through the space with usually a more practical consideration after you've done the math and verified the set of solutions that exist. We want to talk about the transmission ratio. It's kind of a hideous equation here, but that defines the transmission ratio from the input to the output. And it can also be defined by taking the slope of the input and output kinematics. Talked about singularities. These are generally just something to avoid. Causes loss of degree of freedom. Things can blow up. So we try to keep the links from ever becoming straight. In my previous work, I've avoided singularities by 30 degrees. So that when you're speccing that linkage, this would factor back in to its initial configuration. You don't want it to ever be in its range of motion closer to 30 degrees from a singularity. Yeah?
If you're avoiding the singularity, do you actually just put a physical hard stop that it can't go past, or do you do a software limit where it can't go past the 30 degrees? Or
No, it would be in the design. When you're designing it and finding the solutions of linkages that solve your application, you're choosing these link lengths and these angles, and you would choose them in such a way that you never, during the motion of your application, it never came within 30 degrees of a singularity. So it's more like that. So it all has to do, like when you're building a linkage, you have to specify the link length, so it's kind of all of that information. Yeah,
So would you ever put like a motor in more than one of, like where would you put the motor in this case, I guess?
yeah, that's a great question, but you could have a motor driving one link, that's common. Another like way to do this would be to have a motor act on a link and change that link's length. That's called a Hokin's linkage. We've built some machines that do that. So that would be using a screw.
Okay. I was just like, I clicked on the link and I've been like going through some of the examples, so it's really cool, but I was kind of confused like how the motion worked because it seemed like there's multiple, I guess, of like the joint connectors that were like rotating, but not, sometimes one isn't fully going through a full like 360-degree cycle as if like that motor was continuously moving.
Yeah.
So I just didn't really understand like where the motor would be and like how could it just then, like is it being back driven if there is a motor there or like how, I don't know.
You can, I mean, it generally works the same way. You can put a motor on the input, it will drive the output, but it'll drive it under the constraints of this transmission ratio, which is gonna do things like what you're saying. It's gonna fix the relationship.
Do a full rotation.
Yeah, it won't allow it to do that in that case. And that would be normal, like that's okay, that's what they do. But so like one way would be just drive a link, another way would be to drive the length of a link. Those are both possible. And like relatively straightforward. So for example, we talked for a minute about the research example, which I don't think is, I don't have these slides, but the way we did that, the way we actuated this was one of the short link in that little 4-bar linkage of that prosthesis, the short link was on a pulley, with a pulley. So when we rotate that pulley, it rotates that link. And that's how we drove it. We never let it get out of its range of motion that we wanted.
It was cool to see. I didn't realize like they did a bicycle example of like the knee and then the pedals. And
Oh, that's cool.
I don't really understand how that would be like a linkage, but then when you see it, it like makes a lot of sense.
I love it. Everybody look at this, yeah.
Why can't the fact work from L3 apply to L1? Like I could see how the converse is true, but wouldn't like if you try to rotate L3 just cause like L1 to rotate more counterclockwise?
Are you talking about specifically this configuration? This configuration is a singularity, so this would be not something we ever want to see. But right now, its motion, it can't affect it. As it's drawn, it can't affect L1. So like, I would say, don't think about this the way it actually works. That's a singularity that should never happen. If you look at kind of the other examples, so like this would be more normal. So then this is going to apply the torque directly to L1, and that's like a very common type of linkage. I mean, it just works like a transmission ratio. Like you can just imagine it as a set of gears where the transmission ratio of those gears changes as that function.
So, like at the singularity, the transmission ratio kind of approaches infinity, doesn't it? So, but it does give a ton of torque, like, but not a lot of motion.
Yeah. I mean, it does give a lot of torque. It would not give any motion. It does sound right. Cool. So you want to avoid those. And then we kind of like finished up with compound transmissions, where we just take transmissions and stack them against each other. This is like super common. Almost every machine we build does some version of this. In this particular case, in the ballbot, we aren't doing it. We just have one gearhead drive the system. But if we were connecting multiple transmissions in series, we would multiply their efficiencies and multiply their transmission ratios. In your quiz, you're going to do an example of that. Okay, so that was review. Now we're on to new content. So to determine the layout, we talked about lots of aspects of the ballbot, and we haven't talked about how to structure the components around the geometry of the ballbot. So that's what I want to talk about now. This is what I'm calling layout. And this is something you would have to do for building any robot. There's going to be some geometry associated with the task or the machine you're building that you generally have to understand really, really well to be able to understand where the parts should be with respect to each other. So we're gonna do that a little bit. The geometry of the ballbot is more complex and important than usual. Yeah, so the geometry in this particular example is a more sophisticated example than the typical kind of easy machines that we would build. To describe its motion, we need to understand how torque and positions change through the ballbot. That's kind of what we're going to go into. So we need some in-depth descriptions. Torque, motion, applied. I'll say from wheels to basketball. This is important for understanding the layout, but it's also going to be very, very important for control. And so layout and control here are going to be kind of mixed a little bit because of the way that we're going to think about laying it out. And we'll get to that. So it's also critical for control. That's one reason why we pushed layout kind of now instead of going over it earlier. We kind of wanted to be pretty close to control. Okay, so this is our ballbot geometry parameterized by a bunch of parameters that are going to matter. We're going to talk through this. The main design decisions for building a ballbot are three variables. Alpha angle, ball radius, and wheel radius. What is alpha angle? Alpha angle is this. Oh man, this is the issue. Like that shouldn't be there. Oh, okay. I'm gonna try to draw that in then. Alpha is there. 45 degrees. That's RW, that's the radius of our wheel. This is RK. Alpha equals 45 degrees. What is alpha? Alpha is this angle. What is it defining? Yeah.
The degree of contact like on the ball.
It defines the point of contact for the wheel on the ball. Yes, and that is really important. What happens if we increase or decrease alpha? Yeah.
I think like when it increases, we do get more stability, but we also might like lose some useful torque. Like if it approaches like 90 degrees, we wouldn't be able to like roll the ball in any meaningful way. So
Yeah, I think that's right. So let's think like specifically what happens. What happens to so there's a force here, yes? What happens to this force as we change alpha? Yeah.
Decrease because there's less. Well, wait, which are you talking about? Like the contact, like the normal force of the ball on the. It would decrease because the ball is like.
Its weight is fixed. So as we rotate this over, the component that's supporting its weight will get lower and lower.
Yeah.
Because its force, the magnitude will have to go higher and higher. So if we rotate this over, we're basically providing a gain on that force.
But isn't like as it approaches 90, like it'll lose contact and then the force will be 0?
As it approaches 90, its force will approach infinity. And then it would sort of like fall off.
Isn't that like measuring like the contact? And as it approaches 90, doesn't it like lose contact?
It does. Yes, that's true. And the contact loss is an important thing, which we'll talk about in a second. So let's think this is supporting its own weight. So what we want to do is support the vertical component of this thing's mass by 3. So as this rotates, the component that's supporting mass, the vertical component of this force becomes like smaller and smaller and smaller as it rotates over. So now that vertical component still has to equal mg/3.
Okay. Yeah.
So that means its magnitude of that radial forces have to get higher and higher. So So there's one trade that as we change alpha, it's gonna increase that radial force. What do you guys think what will that do? If we increase that radial force, what happens? As alpha is increased, radial force increases. Yeah,
Think you gotta make your motor mount way stronger?
yeah, that's true. So it's gonna have like physical demands on your parts, definitely. Yeah,
Won't the ball move faster, which would make it harder to control?
I think the ball motion is like a separate issue. I think it can be the same. The ball motion isn't constrained by alpha. It's gonna have more friction, so more force, there's gonna be more friction. So that means there's both static friction, so its ability to grip the ball will go up, which is a good thing. We want it to grip the ball, so that's a good thing. But remember, it's rolling on these wheels, and those wheels are, have these rollers that rotate in the other direction. There's friction there too. That friction's gonna go up. So as we increase alpha, we're both gonna get higher radial forces. We're gonna get less likelihood of better ball grip, less likelihood of slipping, but also higher loss in the system. In addition, the stability part. So it does affect stability or at least it affects its lean angle. It's as the ball rotates over, eventually those wheels are gonna lose contact with the ball. It's gonna fall off. So there's a geometric issue about its lean angle that's related to alpha. So what we're gonna say is that alpha is 45 degrees, balances radial force and friction and lean. That is the worst handwriting. Let me try that again. Okay. So larger alpha designs have, let me just finish this and I'll get your question. Larger alpha designs have a greater lean angle. Yep.
I guess I'm still a little bit confused how you said that as alpha increases, then the grip strength also increases because the radial force is greater, but it's also going to lose contact with, how can it be possible for it to lose contact with the ball but also have greater grip strength?
When we're talking about grip strength, we're just thinking about it in its nominal position vertically. When we talk about leaning, we're thinking about like that system leaning over. So both of those would be true. It's dependent on both. Its forces would be dependent on its lean angle and alpha. But as it's sitting vertically,
Yeah.
its force will go up as alpha increases. But then when you start to lean it, it's gonna be.
Oh, okay.
Got it?
Yeah.
Cool. Okay. So this design, 45 degrees, it's very common for ball bots. So in addition to balancing these things, it's actually also a common design. So we felt comfortable making that choice. So that's one of our three decisions. We only have like three decisions to make. Alpha, ball radius, wheel radius. Ball radius, we chose a basketball. We chose a basketball for its size, cost, and texture. So we could build a ball about anything, but we selected a basketball. That defines defines our K. Basketball radius is 119.25 millimeters. Wheel radius, it's our last decision. Our wheel radius, we know what that is. I mean, there's omni wheels only come in certain sizes. So our wheel radius is 47.8 millimeters. now we've made all the decisions to make, this is why this is a little bit unusual, because this ballbot's a very sophisticated system, but the decisions that are made are there aren't a lot of decisions to make, but there's still a lot of modeling and mathematics behind it. Whereas in some other applications, it might be that there's more decisions to make. There's more dimensions you have to choose or layout options. On the ballbot, it's sort of defined based on its math. Okay. There's one other dimension that matters. I'm not calling it a design decision that you have to make, but it's a value that plays into the structure, which is this distance. The distance between the wheel and the motor face, coupler distance. So coupler to wheel center distance is 24.5 millimeters. So now it is fully defined. Does that make sense? Now there's if we were trying to build this motor mount, we have now defined everything we need. This is the circle that the contact points are on. That circle is, circle with radius 84.3 millimeters, and this is RK sine alpha. Where's that guy? Okay. So this, I just want you to know that we're looking at that. There's a circle here where the contact points are on. That's going to come up in a second. And then these are all the decisions we have to make. 3 decisions. Really, sort of no decisions. 45 is a common angle. Makes sense for us. We want to use a basketball. There aren't very many omni-wheel choices. So then all of a sudden, everything is defined. So now if we want to think about we had to provide you guys your motor mounts to position the motors into this geometry. And so we didn't have you guys to do this, we just did it for you so that we could start on it earlier. But this is where all of this comes from. Here's again our alpha, RK, our wheel. Once we add that coupler distance, we know the motor's sitting right there. Just like we gave you that sketch with the motor face on it. So now we know many of the dimensions driven by alpha, ball radius, wheel radius, and I'm saying the coupler, so I'm thinking of that as a constraint. You could actually design this for kind of any coupler length. It's just going to space the mass differently. To design the motor mount sketches, we need to know more about the motor dimensions. Specifically, the shaft is off center by 7 millimeters. Contact point off center. That changes the exact location of the motor face. So at this point, with this information, just from these kind of 2 or 3 slides, you could position that motor face right where we provided it to you. Then all we really did was give you guys all a common distance from the center, this radial distance of these fasteners. And then that made it so everybody's geometries were the same. These dimensions define now your sketches. They're provided. Does this make sense? I think you guys could have done this. So we could have restructured this class and had you guys actually build this part of it, but it would have been, I think, a lot of time and explanation for not a ton of learning. So we didn't do that. We just gave it to you. But this is how you could have done it. Now let's discuss motion and torque transfer. Before that, I do want to show you real quickly our first design ballbot. So this is what we did over summer. We designed 2 ballbots. So one of them is the one you guys have seen a lot in lab. This was our first ballbot we made. What's the main difference? Yeah.
The mounts are under the plate.
Mounts are under the plate. So our first design, we did mounts under the plate. That sort of lifted everything up. And it made these mounts kind of tall. Why do you think we went away from that? Yeah.
More unstable since the center of mass is higher.
Yes. We wanted to lower the center of mass down after having some practice with this. There were two reasons. That was one major reason. What do you think the second reason is? Yeah.
It's like the load on the motor mount. If they're farther, if the motor mounts are taller, then it's like kind of a load.
Yes. And that had a property that we didn't like. Anybody know? Like, it's that concept. These motors, yeah.
Doesn't alpha change?
No, alpha is the same actually. It looks different, but it definitely, it was 45 degrees, yeah. We didn't change it, but it does look.
But the wheels are perpendicular to the mouse.
Yeah, I think so. Oh, okay, so here's what's happening. Like the other thing has to do with the loading is that the mounts weren't stiff enough. They were too compliant. So what's happening there is the mounts are bending, and then that caused also a bunch of trouble because we need those mounts. We need to know the contact locations on the ball for all of this that we're talking about to work out. So that didn't work, so we went away from this. And then we did it like this. Those mounts became much shorter and stiffer. They have much more material in them. And I think all of your guys' mounts are very stiff as well. So like that, I think that was a good choice. So the effect of this is increase stiffness with motor mounts, lower center of mass. So I kind of just wanted to show you this to give you an idea of like, here's two layout examples where we learned a lot from our first layout, and it wasn't really something that we like would have known from like kind of textbook engineering. This we had to build and try, and then we learned like, okay, this was not right, or this is causing more trouble, we switched. And then I think now it's been much better. But that just gives you an example of kind of like how the layout factors in and how we handled it for this ballbot. Any questions about layout and your geometry, how all that was defined? Could you guys have done that? Like what if this lecture had said, okay, now like lab 1, just design that sketch. Could you guys have done that? Given these dimensions? I think so. I think you guys could. I think if you looked at this, it's all in this figure. So like once we gave you this figure, like I think you guys would be able to do it. Okay, cool. In Canvas, under Files for Lecture, Lecture 12 is a sectioned version of the ETH dissertation that we've mentioned a few times. That only includes the stuff I'm about to go over now. So if you're interested in sort of a condensed or shorter version, it's uploaded for today's lecture. All right, talk about the full planar model. When speccing these, the ballbot, we developed a planar model. We kind of talked through that. We did the mechanics, at least a kind of an overview of them. We used those mechanics to get the torque that we needed for a given position profile that we asked the ball to follow back in the speccing process. So that introduced us to modeling the ballbot in one plane. Now we're going to do something different, or also similar. We're going to think of a three-dimensional ballbot in 3 planes, both the two-dimensional planar models that we talked about before, and then one model from above that sort of discusses this rotation. So we previously developed a planar model. We're going to build on that to describe the 3D motion and torque of the bot. We project a 3D ballbot into 3 planes. XZ YZ, and XY. Each plane contains one virtual motor, or one virtual wheel. This was from our kind of specking lecture. We were driving this wheel. We used that from position profile to get torques on the motor. Now we're here. Same exact concept. Ballbot, but now we have two planar models. It has three wheels. Two wheels are located directly beneath the center of mass. And then the third wheel is located at an angle that rotates it around the z-axis. This simplification is helpful analytically. So we're gonna use this a lot. Before we keep going on this, I want to go through a few assumptions, okay, that are associated with this model, with this understanding. First is no slip. Contact points at the wheel, ball, and ball ground interfaces do not slip. What does that mean? That the velocity on the very bottom of the ball is. Yeah, what is it? 0. So the velocity at the ball ground interface, 0. Okay, another assumption we're gonna make is there's no deformation of the ball. So we're just not gonna include that. So there's basketball, there's weight on it, it's pressurized. We're not gonna allow for any deformation of the ball in our mathematics to keep it simple. No ball deformation. But everything will really just be about RK. The radius of the ball. Okay, now, just to kind of make sure we're on the same page, considering a ball rolling with some velocity. What's the tangential velocity from rolling of a ball or wheel? Yeah.
Just theta dot r.
Yep. R theta dot. What's the velocity at the top of the ball? Based on what you see on that page. What did you say? And more generally, I'll leave it as x dot plus r theta dot. But what does no slipping mean? Like what does no slipping mean in terms of x dot and r theta dot? They're the same. So if it's not slipping, so we see x dot top is going to be x dot plus r theta dot. And no slip, this means r theta dot is equal to x dot. So that makes your original answer correct. Awesome. Okay, let's just kind of make sure everybody is good with this model. Each plane has 2 degrees of freedom. Rotations of the chassis, and ball. So let's think for a second about, actually let me fill these blanks first and then we'll do that. So this is x, z, and y, z. Planes have a single ball or single wheel under the center of mass. So both these planes have a wheel directly underneath, so on the very top of the ball, there's a virtual wheel in both planes. That's the XZ and YZ planes, they're going to be very similar. The XY plane contains a single wheel to rotate. The ball. Okay. If we're thinking about balancing and rolling, which planes matter? Do all the planes matter? Yeah.
The horizontal plane doesn't matter.
Which one?
Well, the XY plane doesn't.
The XY plane doesn't matter. It ends up being irrelevant. So what we want to do is balance it. We don't care if it spins. It actually can spin. We're not really worried about that. But we're going to end up defining it to stay at 0. But we really care about the XY planes, the XZ and YZ planes, and not the XY plane. So XZ and XY planes are for motion and balance. XY plane is sort of irrelevant. Okay, so now we have a model of the ballbot's motion. Yeah.
You wrote XY twice.
Did I?
Like, you have XY is relevant.
Oh, this should be Z. You mean here?
Yeah.
Yeah, there is.
YZ.
Yes, it should be XZ at YZ. Thank you. Okay, so now we have an understanding of how we're going to model this ballbot using 2 planes essentially that we've talked about already. So we kind of know how to model a planar ballbot. We've separated it. Each plane has 1 wheel, and we have a third plane that rotates it around the z-axis, which we don't really care about. The torques and motions from the virtual wheels, these wheels, are they the same or different than the torques and motions of the actual wheels? Different. So now we need some understanding of how to convert torque and motion from our planar understanding to the actual 3D ballbot for execution and implementation. Let's talk about torque transfer. Okay. How does motor torque get transferred to each plane? That's what we're going to talk about right now. We're going to need to understand how applying torques to the ball through our motors transforms into the torques on the YZ and XZ planes. Okay. What I'm showing here is a top-down view of the ballbot. But what we're looking at is each one of these is a contact point. So the torques provided by those wheels are these vectors, T1, T2, and T3. The torques in our planar model are going to be Tx and Ty. So we're going to be analyzing the system in the terms of these planar models, X and Y. But we're going to need to transform those torques to the torques on the motors 1, 2, and 3. The torques on the motors are going to end up being, the way the torque is applied to the ball will be F cross R. We'll get to that. So that's what we're looking at, top-down view of the ball. And when I said there's a circle that all the wheels are on, that's this circle, where this dashed line is the actual ball circumference. So the wheels, because they're at 45 degrees, are sitting up away from the ball circumference this way. So let's kind of talk through this. We want to look at how geometry affects resolving torques between the coordinate axes. Planar torques are around the x and y axes. The wheel torques are T1, T2, T3. What's the, I guess it's here. Okay, so this, the radius of the contact circle, that's RK sine alpha. Another decision that we've made to simplify or make things easier is to align the torque of one wheel with the torque of one axis. So the y-axis and the torque from motor one are aligned. And if you remember the slide I showed yesterday, it had to do with this alignment. We were talking about aligning, that's why the orientation of your pico matters. We aligned motor one torque to be along the y-axis. Let's define that these are 120 degrees apart. Okay. Motor one's torque is aligned along the y-axis. Does that have any consequences? Does that affect what happens to the motor? What we're asking the motor to do? So what we're going to do is we're going to be looking at the way the ballbot is moving and leaning in these projected two planes. We're going to look at that and convert the torque required to write these two planar models back into this 3D model. Does the fact that we aligned one motor's torque with one of these planar axes, does that affect what the motors are going to do or the demands on the motor? Yes. It means that one motor is kind of taking all of the torque from one axis. So it's basically like that original model we did, where we had one, when we spec'd this motor, we did it from a planar model, and we were like, well, really there'd be 3 wheels, but there's only 1 wheel here, so this is gonna be a conservative estimate. Remember that? We're glad we did that, because now we've defined the system to actually behave that way. So if the ball was rolling, for example, in the y plane, the motor one will take the torque of that. So this says, will this have consequences? Yes. Motor one will have more torque. Because we're going to take the torque from the x-axis and split it between 2 motors. But we're not going to do that for the y-axis. And then this says, we planned for this. By originally speccing our motor to be capable of it. Does that make sense? Okay. Now I want to talk about like the wheel contacts. We want to actually define the wheel contacts. What are the locations of the wheel contacts? How can we use that to talk about the force and the torque? So this is just our general expression for torque. We're going to say torque from the wheel is going to be the radius RWI cross FWI. So that's this, those forces, and these radii. So we need descriptions of those radii. This top expression is written around the motors, 1, 2, and 3. The bottom expression is written around the planes, x, y, and z. What is, let's say R, W, Y. That is the radius of the contact point on the y-axis. It's just RK. It turns out it's going to be that for all of them. All the forces are acting on the radius. I think that should be sine alpha. There should be a sine alpha in there. But anyway, I'll come back to that. And then the z-axis. That's their radii and the z-axis, which you can't see in this figure. And it will end up coming into play if I had defined it. These are the virtual contact points. So these contact points don't actually exist. The real wheel contact points do exist. This is where the sine alpha is. Now I'm going to define the locations of these points. RW1, RW2, RW3. Okay. So this defines the contacts, the radii for the contacts in the real world. Yeah.
For the matrix, is it XYZ going down?
Yes. Where do these come from? Like, why are there these? We have sine and cosine alpha, that makes sense, they're gonna be in there. But what are those other angles? Where do they come from? Yeah.
Sine cosine of like 120 degrees.
Yes. Yeah, it comes from the other geometric aspect of this, which is the 120 degree spacing. And instead of including that as an angle and putting sine and cosine, we just put the actual values for you because they're known and constant. Okay, so this tells us the real and virtual contact points. we're gonna stop here. I'm gonna come back to this next lecture, we're gonna continue it. We're gonna continue the wheel, the contact points, torque, and we're gonna do motion. We're gonna describe the motion a little bit more in depth. Similarly, it will be equations, some of the equations you will have seen before, we just didn't talk about where they came from in the beginning. So now we're kind of talking about some of the things we saw during the specking process, but giving you some depth. Okay, so we're gonna pause here. We're gonna spend the last 20 minutes doing a quiz.